It's really pretty amazing watching how these language models are evolving, isn't it? I mean, first it felt like it was all about just getting the next word right,
Uh-huh.
but now it seems like the cutting edge is pushing for models that actually, understand things, maybe even plan ahead.
Absolutely. That next token prediction, NTP, it's been the bedrock, no doubt. But its limits are definitely starting to show, especially when we want AI that gets the nuances of language or can reason more like humans do.
Which, yeah, brings us right to what we're digging into today. You sent over that paper, Looking Beyond the Next Token.
Right?
And it introduces this method, Trelawney, which seems to hit these limitations head on. You mentioned specifically wanting to get a more academic handle on it, really zeroing in on what makes it innovative.
Precisely. Your notes highlighted that need moving past just a summary to really dissect what's new here methodologically. So, yeah, our mission today is exactly that. Unpack how Trelawney offers this novel, data-centric way to train models and pinpoint where that innovation really lies.
Okay, let's do it. So, for ages, standard practice has been this next token prediction, NTP. And a key part of that is something called teacher forcing, right?
Exactly. That goes way back, actually. Williams and Zipser talked about it in 89. The basic idea is during training, you feed the model the correct previous token at each step, not whatever it might have predicted itself.
Okay, yeah, that makes intuitive sense. You're guiding it, keeping it on track during the learning phase.
And it has real benefits. It speeds up training significantly. It makes the gradient updates, how the model adjusts itself much more stable, which is crucial. And importantly, it lets you parallelize the computation. You couldn't train these massive models otherwise.
But like you said, limitations. This 2024 paper by Bachman and Nagarajan dives into those. What are the main problems they flagged with this approach?
They point out several key issues. A big one is learning long-range dependencies because the model always gets the right input. It doesn't always learn to connect ideas that are far apart in the text.
Ah, so it gets good at the local stuff, but misses the bigger picture, the overall flow.
Exactly. It can end up just latching onto these local patterns, surface correlations. They call it the clever Hans cheat, which I think is a great name.
Clever Hans. Like the horse.
Yeah, the horse that looked like it could do math but was just reading cues from its owner. The model looks smart, predicting accurately based on immediate context, but it hasn't really grasped the underlying logic or relationships. It's just copying, essentially.
Okay, that lack of deeper understanding would definitely be a barrier to complex reasoning or planning.
For sure. And that connects to another issue they call the indecipherable token problem. Because later tokens are often easy to predict once you have the correct preceding ones, the really crucial decisions made early in a sequence don't get a strong enough learning signal, a strong gradient. The model doesn't learn why those early choices were so important for the final outcome.
Hmm, that's subtle. And then there's exposure bias too, right? Something about training versus the real world.
Exactly right. Exposure bias is this mismatch. During training, the model always sees the perfect history, the correct sequence of previous tokens. But when it's actually generating text, at inference time, it has to rely on its own previous predictions, which might be wrong.
Ah, so errors can build up. One mistake leads to another.
Precisely. That discrepancy means the efficient training setup doesn't quite prepare the model for the messiness of generating text from scratch. It hurts robustness.
Okay, so NTP with teacher forcing, it got us far, efficient, but maybe hits a ceiling for really sophisticated stuff, which is where Trelawney comes in. The paper calls it data centric. What does that mean here?
Yeah, that's a really key distinction they make. Instead of redesigning the model's architecture, like changing the neural network itself or messing with the core training objective, Trelawney focuses on reorganizing the training data.
So changing the curriculum, not the student's brain, so to speak.
That's a good way to put it. It contrasts with other ideas like predicting multiple tokens at once or using different model structures like that transformer variant you mentioned. Trelawney says, let's keep the model and the basic training setup, but give it smarter data.
Interesting. So how does it actually reorganize or augment the data? What's the trick?
The core idea is interleaving the normal training sequences with these special look-ahead tokens. TNT, think of them like brackets. And inside these brackets, they put information from later in the original sequence. Figure 1 in the paper shows it quite clearly.
Whoa, okay. Future information shown before it happens in the sequence. That's kind of mind-bending. Where does that future info come from, and how do they decide where to put it?
Well, that's part of the flexibility. The paper says where you put the TNT tokens and what exactly goes inside them can be random, actually, which surprisingly works quite well sometimes. Or it can be based on specific knowledge about the task. The hypothesis, the core idea, is that showing the model this future context helps it learn those tricky long-range connections and, crucially, helps it develop a kind of planning ability.
Makes sense. If you know where you're eventually heading, it probably helps figure out the steps to get there. The paper mentions specific ways to do this augmentation. First one is copying. How does that work?
The copying schema is pretty direct. You literally take a subsequence of tokens, let's say y, from index s to s plus k from after the point d, where you insert the t token in the original sequence, then you just copy that subsequence ys dot s plus k right between t and t.
So just giving it a direct preview, a snippet of what's coming later. Does it matter which snippet you copy or where you insert it?
It can, yeah. The paper talks about decision points, places in a sequence where things could go different ways. Putting the future snippet before one of those points could be really helpful, and the copy bit might represent key future tokens that signal some goal. But they also say for general language modeling, just picking those parameters D, S, and K randomly works too.
Huh. That idea of decision points is really interesting. Even if they aren't marked, maybe the model learns to recognize them by seeing these future hints. What about the second method, positional information? Why is that needed?
Good question. The issue with just copying is that the distance, the number of tokens between where to insert the hint, D, and where the copied info originally came from, can vary a lot between examples.
Ah, okay. So if two sequences start the same way, but the relevant future bit is like 10 tokens away in one and 100 tokens away in the other.
Exactly. That could confuse the model. It might struggle to figure out the timing, the relevance of that future snippet. So the positional information schema adds extra context, they call it ZFKZ, along with the future token Z.
And how does it add that context?
They give a neat example using natural language, like inserting the phrase, I want the kth sentence from here to be Z. So K gives the relative position, and Z is the future text itself. This helps the model understand when in the future this piece of information fits.
Got it. So it's not just what, but when. And they mentioned the future text Z doesn't even have to be an exact copy. Paraphrases work too.
Right. Or just relevant information. It adds flexibility. And using natural language for that positional context Z is clever too. It lets the model use its existing language skills, and it also means a user could potentially specify goals in a more natural way.
Okay, so we're creating this augmented data with T, future info, sometimes positional cues. How do you actually train a model with this mix? Do you just throw it all together?
Pretty much, yeah. You train on a mixture of the original data and this Trelawney augmented data. There's a probability, P, that controls how much augmented data you use. But crucially, they stick with the standard optimization method, cross-entropy loss with teacher forcing.
Oh, so you can still use all the existing efficient training pipelines. That's a big practical plus.
Definitely. It avoids reinventing the wheel on the optimization side. There is one key tweak to the loss function, though.
Right, I remember reading something about the T token itself.
Yeah, exactly. Making the model predict the opening T token isn't really useful. It's an artificial insertion. Penalizing errors on it could just add noise. So they mask the loss for the prediction of T. You don't calculate loss there.
Okay.
But importantly, they do calculate loss for the closing T token. Predicting when the future information ends is still a useful signal for the model to learn.
That makes perfect sense. Focus on the content and the end, not the artificial start marker. Okay, training makes sense. What about actually using a Trelawney trained model for generating text? Are there new ways to do inference?
There are. First, you can just do standard autoregressive generation one token at a time, like usual. And the hope is that the Trelawney training implicitly made the model better at planning, even in this standard mode.
Okay, so check if it just got generally smarter.
Right. But the really novel part is what they call T generation.
T generation, how does that work?
So when you're generating a sequence, you can decide to insert the T token at some point, maybe a point you think is a key decision. Then after T, there are two main possibilities.
Okay.
First, you can just let the model generate whatever comes next, including the sequence Z between T, and then finally generate the T token itself. In this mode, the model is essentially creating its own little plan or predicting its own future steps.
Wow, okay. So the model can generate its own internal plan on the fly as part of the output? That sounds powerful. What's the second option?
The second option is, instead of letting the model generate the Z part, you, the user, provide a specific sequence Z that you want to appear in the future. You basically tell the model, okay, generate up to here. Now here's the plan, Z, I want you to follow. Now continue generating after T.
Ah, so that gives you really fine-grained control over where the generation is headed long term. You can inject specific goals or steps.
Exactly. It offers a precise way to steer the output. And another nice thing they point out is that this T generation works with any standard decoding algorithm, greedy search, beam search, sampling. You don't need special decoding methods.
Right, unlike some other approaches trying to achieve similar control. Okay, the theory sounds solid and the inference methods are interesting. How did they test this? You mentioned synthetic and natural language tasks. Let's start with synthetic.
Yeah, they used synthetic tasks first, really controlled setups to isolate Trelawney's effect on planning and control. The first one was the star graph problem.
Okay, I remember that. It's about finding a path in a specific kind of graph, right? With a tricky early decision.
Exactly, a directed graph, start node, goal node, and a bottleneck early on. For Trelawney, they augmented the training data by inserting a future sub-goal, basically a chunk of the correct path, z between t and t. They tried two versions, Trelawney fixed, where z was always the same sub-goal, and Trelawney random, where z was a random part of the future path.
And what did they find on this star graph task? Did Trelawney help?
It did, quite significantly. First, even just using standard generation, the Trelawney trained models were better at finding the path than the standard NTP models, so it seemed to improve implicit planning.
Okay.
Second, using T generation, especially letting the model generate its own sub-goals, helped even more on longer, harder graphs. And using user-provided goals also boosted performance, showing that controllability aspect.
Makes sense.
And here's something interesting. The Trelawney random version actually did better than the fixed version on the longer paths.
Really? Random was better. Why?
They suggest it might act as a kind of regularization. The randomness prevents the model from just memorizing one specific sub-goal pattern, maybe making it generalize better. Oh, and they also found larger models benefited more from Trelawney.
Fascinating. Strong results on a task designed to challenge NTP. What was the other synthetic task? Something about algorithms.
Yeah, algorithmic reasoning, they used the CLRS text benchmark, specifically the task of finding strongly connected components in a graph. This requires backtracking using Tarjan's algorithm.
Okay, another task needing complex sequential reasoning. How did they apply Trelawney here?
They augmented the data by taking a complete step ties from the algorithm's execution trace and inserting that between T and T, usually after the second state in the trace. Again, they had two versions. Trelawney rule-based, where they always inserted the step corresponding to the first change in the trace, and Trelawney random, inserting a step from a random point in the trace.
And the results on this one?
Also quite revealing, Trelawney random consistently improved performance in predicting the final answer, both with T generation and even just standard generation.
Okay, random wins again.
Yeah, and surprisingly, the rule-based approach, which you might think would be more helpful, actually performed worse than the baseline sometimes.
Huh. That really reinforces the idea that maybe that random exposure to different future states is key.
It seems that way, yeah. It suggests the diversity in the look-ahead might be more beneficial than a single fixed strategy.
Okay, so across these controlled synthetic tests, Trelawney clearly shows benefits for planning and control. What about natural language? That feels like the real test. They used story generation.
They did. They used the Tiny Stories dataset, focusing on generating coherent stories that achieve a specific goal given at the start. The augmentation here involved inserting a future sentence from the story between T and T, sometimes with positional info like the next sentence should be, or explicitly using sentence numbers.
And how did they judge if the stories were any good or if they reached the goal? That seems harder than checking a graph path.
For sure. They used GPT-4 as an evaluator. They had it compare stories generated by Trelawney models against a baseline model that just used few-shot prompting, giving it a few examples in the input. They asked GPT-4 which story was better overall and which one achieved the goal better.
Okay, using an AI judge, what did GPT-4 prefer?
The results were pretty strong. When the models were explicitly trying to reach a goal using T generation, GPT-4 preferred the Trelawney stories a whopping 76.5% of the time compared to the Q-shot baseline.
Wow, okay. That's a big difference.
Yeah, it really suggests Trelawney helps with controllable generation in natural language. And even in standard generation mode, the Trelawney stories were preferred over the standard NTP ones about 40% of the time, often specifically because the endings were more coherent or relevant to the beginning. They also found that giving explicit positional info gave even better control.
And crucially, did this new training mess up its general language abilities? Like, could it still just predict text normally?
Good point. They checked that. They measured perplexity, which is a standard measure of language modeling quality, on a benchmark dataset, Wikitext. And they found Trelawney training didn't significantly hurt perplexity.
Okay, so it learned this new planning skill without forgetting how to just be a good language model. That's important.
Definitely. So yeah, from synthetic graphs to little stories, Trelawney seems to deliver real improvements in planning and control without breaking basic functionality. It really does feel like looking beyond the next token opens up something new.
Absolutely. It feels like the real innovation here, the core academic contribution, is this data-centric approach, tackling those fundamental NTP limits by being clever about the data, not just throwing more parameters or a whole new architecture at it.
Exactly. By restructuring the training input to include future context, it pushes the model to learn these long-term dependencies and planning skills in a way that leverages existing architectures and training methods, That's the innovative twist.
And they have ideas for where to take this next, right? What future research directions did they mention?
Yeah, they outlined several promising paths. One is obviously scaling this up, see if these benefits hold during large-scale pre-training on massive data sets.
Makes sense.
They also talked about integrating it with reinforcement learning, maybe for even more complex planning. Another cool idea was developing ways for the model to learn when it's best to use this look-ahead capability, maybe based on how uncertain it is.
Ooh, like it decides for itself, this looks tricky, better peek ahead.
Something like that. And of course, testing it on more complex natural language tasks and maybe encouraging it to generate more abstract plans, not just copies of future text.
It definitely feels like early days for a really promising idea. Trelawney offers this genuinely different angle on training language models, breaking out of that strict next token only mindset.
Totally agree. It's a significant innovation, focusing on data as the lever for improving planning and control. It really highlights that big advances can come from smarter training strategies, not just bigger models.
So, for you, our listener, the key takeaway here is that Trelawney is this novel, data driven technique that seems to genuinely boost language models' ability to plan and follow instructions, which is a major step forward. The innovation is all about that clever data augmentation.
Right? It's not about changing the model's core design, but changing what it learns from.
And it really makes you wonder, doesn't it? If techniques like this become widespread, how does it change how we interact with AI? What becomes possible when models can inherently make and follow long term plans?
That's the provocative thought, isn't it? Thinking about AI that doesn't just react, but plans. It opens up a whole new design space for interaction and application.
Definitely something to mull over. And if you want to get into the nitty gritty, we absolutely recommend checking out the Looking Beyond the Next Token paper itself and the other papers they cite. Lots to dig into there.